Good morning, dear students. Today we are going to start a new chapter, that is Principle of Mathematical Induction. It is a very easy chapter, and whenever you are solving the question in this particular question chapter, you will feel like it is very easy. Why? Because question is given in such a manner that you have to prove the formula only, or likewise. So we'll move to the lecture now. So, before starting to principle of mathematical inductions, let us see the statements. We have statements, two statements over here. First one is A, that is saying that Socrates is a man, and another one is in this here, in this statement, all men are mortal. So, therefore, we can deduce that Socrates is mortal. Socrates is a man, all men are mortal. Therefore, Socrates is mortal. Now, mathematically, we will consider one more statement, that is statement number 2, and in that statement, we have three sentences over there. First one states that 8 is divisible by 2, and another sentence is saying that any number divisible by 2 is an even number. So therefore we can deduce that 8 is an even number. Why? Because 8 is divisible by 2, and any number which is divisible by 2 is an even number. So we can say that 8 is an even number. So this is fundamentally known as deduction, or deduction method, or we are deriving that thing. So given a statement to be proven, often called a conjecture or a theorem in mathematics, very deductive steps are derived and a proof may or may not be established. That is, deduction is the application of a general case to a particular case. This is a very important thing. General case to a particular case. Deduction is nothing but this one only. What you are doing is, this is general case, this is general case, and using these two, what you are doing is, this is particular case. Similarly, over here, this is general case, this is general case, and using these or each sentences or cases, what you are doing is, you are deriving this particular case. So deduction is nothing but we solve deductive reasoning likewise. Now we will move to the next point, that is this point, that is inductive reasoning depends on working with each case and developing conjecture by observing incidences till each and every case. Thus we can say the word induction means generalization from particular case or fact. Induction is nothing but, this is a very important thing. The entire chapter is based on this particular phenomena only, that induction means the generalization from particular case or fact. So what we will be doing is, we will induct, or we will make generalization from particular case or facts. So basically what we are doing is, whatever the formula you can see in the mathematics is nothing but the generalization form only. Some particular cases are given to you, but that is different thing. But in general, just like a plus b whole square is equal to a square plus b square plus 2ab. So it is just like that only. So what we are doing is, we are putting value 1 over there, then k plus 1. We will check that, and later in this video only, later on, we will come to know how to solve the questions also. In algebra, or in particular or other branches, in branches of mathematics, there are a lot of many things which are expressed in the form of n, where n is some integer. So in that particular thing, to uh, to prove statements, the well-suited principle that is used based on the specific technique is known as the principle of mathematical induction. So we have so many results in form of n, and we have to prove that statement, and we have to follow well-suited principle used based on the specific technique. And this is the technique we will discuss this also, known as the principle of mathematical induction. And what is the principle of mathematical induction is, so this is the working algorithm, this is the method which we are going to follow for the entire questions to solve. So suppose there is a given statement p of n involving the natural number n such that first one states that, and first one is the statement is true for n equal to 1, or we have to find out this as equal to true. Definitely we will get that. And in this statement 2, we have to, if the statement is true for n equal to k, if n equal to k, where k belongs to positive integer, where k is nothing but the positive integer, then the statement is also true for n equal to k plus 1. If this is true, then the statement will be also true for n equal to k plus 1. We have to prove this considering this as a true. So this is a working model. Then truth of p of k, that implies truth of p of k plus 1. So basically this is written in words, and this is mathematically. If this is true, that implies this is equal to true, right? Then p of n is true for all natural numbers, or all natural number n. So basically in property 1, what we are getting is simply a statement of fact we will get. Therefore we can say n equal to 1, it is true. Or if the statement is starting from, let us consider where n is greater than or equal to 4, if it is saying like that, then we have to put, or we have to start n equal to 4. At n equal to 4, we have to start instead of n equal to 1. If any statement is given and the condition is there, if there is no condition, we will start n equal to 1. If there is a condition such as that statement holds good for n equal to or n is greater than or equal to 4, then what we are doing is we will start solving from n equal to 4. Likewise, and property 2 is conditional property. This is conditional property. If this is true, n equal to k, then definitely it will be going to true. We have to prove this one. So now let us solve some questions in this. Now we will see this example. To prove 1 square plus 2 square plus up to n square, and that is greater than n cube divided by 3 for all n belongs to n. N is nothing but, this is n we are considering as in general, and this n is natural number. So this n belongs to natural number. So we have to prove that this is sum of square of all natural number is greater than n cube by 3. We also know that sum of square of that all natural number is equal to n into n plus 1 into 2n plus 1 divided by 6. Definitely that is greater, that is equal to that, but that number is greater than this one, as we can see there. Now coming to the solution, let p of n, we have to consider this as p of n be given statement, and that is nothing but mathematically we can represent P of n such that 1 square plus 2 square plus 3 square plus up to n square, that is greater than n cube by 3. That is n is a natural number. We note that P of n is true for all n equal to n. If we put n equal to 1, that means it will become 1 by 3, and here this is the first term we will consider, and thus this first term is 1. Definitely 1 is greater than this 1 by 3. So it holds good, or it is true for n equal to 1. Now assume that P of k is true. So if this is true, that means 1 square plus 2 square up to k square, that is greater than k cube divided by 3. Let us consider that as a first equation. We shall now prove that P of k plus 1 is true whenever P of k is true. So we have to prove that P of k is true. So what we have is, we have this one, and what we are doing is, this is kth term and next one is k plus 1th term. So this is the thing we have from 1. We have taken this directly, and what we are doing is, we are adding on the both side k plus 1th term over here. So this is definitely on the both side we are adding k plus 1 whole square. Now it will become, directly we can say that I'll take 1 by 3 common from this side, and now it will become k cube plus 3 times k square. I'm opening this bracket also, 3 times k square plus 6 times k plus 3 that is equal to 1 by 3 k plus 1 whole square plus 3 times k plus 2, and definitely this is greater than this value. We can see from here only, right? Okay, then therefore P of k is also true whenever P of k is true. Hence by mathematical induction, P of n is true for all n belongs to n, that is natural number. So one can find out the values over here. So you can put any value over there, 1 2 3 4 5 x y z, whatever you want, any natural number you can put, and you can justify whether this is true or not. We know that this is one of the formula you can say, so it holds good. Now the next question is, prove that 7 power n minus 3 power n is divisible by 4 for all n belongs to positive integer, that is represented by z plus or I plus. You can choose any one of these two. Both are good one, and both are true. You can use any one, z plus or I plus. Okay, now we will move to the solution. We can write P of n, that is 7 power n minus 3 power n is divisible by 4. Now we note that P of 1, that is 7 power 1. What we have to do is, we have to put n equal to 1 over here. So now it will become 4, which is divisible by 4. Thus P of 1 is true for n equal to 1. So first of all we have to prove all the time for n equal to 1. And after that what we are doing is, we will consider P of k be true for some natural number k, that is P of k, that is 7 power k minus 3 power k. I have to replace this n by k is divisible by 4. I am assuming this is true. So if this is true, then I can write 7 power k minus 3 power k as equal to 4d. Why? Because it is divisible by 4. So I am writing 4d, where d belongs to natural number. So now we can we wish to prove that P of k plus 1 is true whenever P of k is true. So P of k plus 1 we have to find out. So for that what we are doing is 7 power k plus 1 minus 3 power k plus 1. I have replaced n over there. In the question you can see n is written over there. So what I am doing is I have to prove for k plus 1. That's why I have replaced n by k plus 1. So now this is equal to what I did is I added and subtracted 7 into 3 power k. 7 into 3 power k I subtracted and later I added this number only. So there is nothing as a big difference. This is the same only. I took common 7 from these two terms. I took 3 power k common from these two terms and I got 7 into 7 power k minus 3 power k, and this is nothing but we have already took that as equal to 4d. Now this is true. We are considering this is true and this is divisible by 4. So we will consider this as 4d, and 7 minus 3, this will give us 4 only. So now it will become 7 into 4d plus 4 times 3 power k. Now I took 4 common from both the term and it will become 7d plus 3k. Now looking into the last line, we can say that whatever we have considered, that is 7 power k plus 1 minus 3 power k plus 1 is divisible by 4. If we consider what we consider, if we consider that this is true or this is divisible by 4, then this two terms is also divisible by 4. Thus P of k plus 1 is true when P of k is true. Therefore, by principle of mathematical induction, the statement is true for every positive integer. You have to mention the last line in each and every solution over there to get the full marks. Likewise, you have to solve each and every question and go for the exercise now.